F and P of U, where the set V correspond to the endogenous or observed variables in the systems. The ones that, again, observe are the ones that you can measure. Then we have the set V, V1, V2, Vm. Now we have another set U, U1, U2, Um, that are the exogenous, or exo from outside, endo from inside, that are the latent or the unobserved variables in the system. Now, after having these two, this partition over the variables of the universe between observed and not observed, you have the set of F that are the functions or the mechanisms that determine each of the VI variables, each of the observed variables or endogenous variables VI, this one. You have this function or this mechanism Fi, such that takes as argument. By the way, can you see my mouse? Just to double check. Okay. The VI, there is this mechanism Fi that takes two inputs, or two qualitatively different, two sets. One is called PAI, that are the parents, that is a subset of the observables, and the other is UI, that is the subset of the unobservables. Then it goes PAI, the values of these guys, PAI and UI, goes through the transformation Fi and determines the value of VI. A bit of notation here, introducing kind of, first I will use bold, usually for sets, big variables for caps for the variable, and small non-in-caps or small non-capitalized as the specific value taken by the variable. And I will try to be consistent. It's already not consistent here, but I will try to be consistent as much as I can. But you ask a question if it's not clear. Now, okay, this is the set of collection of mechanisms that are related in some way, the observable, a subset of the observable and an observable with some other observed variable. And then we also have the first three bullets here is essentially describing a deterministic system. It's almost like a Newtonian type of physics. And the fourth one, given that we have uncertainty and variability in the universe or in the system, you have this probability mass. PU is a probability distribution over the exogenous variables U. And you have some kind of sprinkling, or you have sharing some kind of probability mass across each configuration of the unobserved variables U. And this is the system. It turns out that the system that seems quite general. This will be our data generating model, trying to that I think can describe most of the situations that we have. There is axiomatic characterization for systems like that. For example, some of the main references here is Gales and Pearl 98. Gales is a student by Yuda Pearl. There is another paper by Joe Halpern in Cornell, 1998 as well, axiomatizing systems like that, and essentially most of the theorems, I think all of the theorems that we have follow from these axioms, and also for a kind of modern take or a discussion about these systems. Check also the chapter Bareinboim et al. In 2020. This is the last one is the RC. I strongly recommend it as a kind of survey if you are trying to understand what these systems are. It's a chapter, the R60 in my website. Now I would like to connect with one important result that connects the SCM-M with the causal diagram G. I would like to introduce what is a causal diagram. Then every SCM-M, once it's fixed in the world, induces a causal diagram G, represented as a directed acyclic graph DAG where each VI in V is a node, and there is an edge VI to VJ if VI is in the parent set or argument in the function of J or Fj. Here, our example in the right, the set of visible or observed variables is A, B, C, D. The set of unobservable is U. Now we have two functions here, one for each of the, at least I'm showing here, one for each, one for D and one for E. We should have, there are four in reality, I'm just showing that. Now, note here that A and B are arguments, observed arguments in the F of D. Then we add the arrow from A to D, another arrow from B to D. Now there is another, C is an argument in the function of E, then we add the arrow from C to E. Also in the construction of the causal diagram, this is a causal diagram or a DAG, which is a DAG that is more refined in the sense that there are also bidirected arrows. We have a combination of directed and bidirected, where a bidirect edge vi dot dot bidirected dashed vi to vj is there if the intersection between the parents, unobserved parents of vi and observed parents of vj are not empty. In this case, we can see that they share the same U, unobserved U, then we'll add a bidirected arrow between D and E. Is encoding a latent, unobserved common cause. Now, putting these pieces together, this is the graph that we end up getting from the system that we described above. Then you go kind of pairwise way and you get the system. Then result here, again, each SCM-M induces a causal diagram G. Now I write to try to give an example associating the SCM-M with the causal diagram in the context of fairness. This is the Berkeley admission case. Students apply for the university's admission, that's the variable y equal to 1, they have admitted 0 otherwise, and choose specific department to which they want to join. D equal to 0, let's say that is for sciences and engineering. D is equal to 1 is for arts and humanities. For the purpose of discrimination monitoring, gender is also recorded and not make that available for us as the data analysts in this case, where x is equal to 0 is for female, x is equal to 1, sorry, x is equal to 0 is for male, x is equal to 1 is for female. Now, but this is the reference here, the first reference in this particular case, but the Cal, I believe, at all. In this side here, we are showing this SCM-M star such that we have this x. Again, x is the gender. There is the function that may be biology here, f of x is deciding the value. Ux maybe is the set of unobserved factors that may be the genes of the parents. Again, it's unobserved, we don't have, but there is this kind of mechanism in nature, and maybe the baby will come out with some kind of x is equal to 0, x is equal to 1, depending on the gender. You have also a variable D here that is which department the person is applying. Then you have the mechanism f of D, maybe the mind of the person that takes into account or will change depending which x the person have, or potentially will change depending on the x that the person will have, and also U sub D. U sub D in this case is all other factors in the life of the person that is not gender, that may be leading to this decision of applying to the sciences versus applying for the arts. And you have the variable y here, whether the person will be or not, or whether the individual will be admitted or not. That is a function of, possibly a function of gender, the department that's applying, and U sub y, that is everything else that is in the application of the person, or everything else that is in the mind. This f sub y is under the control of the admission committee that you could have in the university. Now, and there is a probability distribution over all the set of unobserved factors, Ux, Ud, and Ui. Now, in this part, again, this left side here is the truth that is unobserved. Now you can construct the causal graph. You already have a constructive method of getting the causal graph. Here we go. Now we'll go to one by one, and you see first, I didn't write here, but Ux, Ud, Ui are all independent. Then there is no bidirected arrow. It seems that there's no bidirected arrow in this particular system. Now we go one by one and check who is the argument of whom. Now observed argument, given that you already did the job with the unobserved one. Now the x, there is no observed variable that is affecting or the argument of x, then there is no incoming arrow to x. For the variable d, there is the x is possibly argument of d. The department choice is changing based on gender, then you add an arrow from x to d. Also, for the variable y, x and d are possibly affecting the admission of the person. Then there is an arrow from x to y, from d to y. Then this is our causal, and that's it. That's the causal diagram. There is some type of coarsening happening between this side here and this graph, in the sense that here we don't have the particulars of the functions that are happening here that are instantiated. Again, here I'm putting a non-committal way, whatever the form is for the M star. In reality, there is some particular form there. We are just picking one here, Drago and Justin. The X, for example, the f of x could be some type of f of x and the ux could be some type of transformation that is Bernoulli 0.5. Maybe in this population we have 50-50 between males and females. For the department here, you have 0.5 and we have 0.5 and you have plus lambda x, which means that depending on if the gender is equal to 1, if this lambda here is different than 0, then let's say that lambda is positive, then there is a higher probability of the female applicants being applied to the arts. That is this d being equal to 1 if x is equal to 1 and lambda is positive. If lambda is negative, it's the other way around. There's a higher probability of they are being applying for the science and engineering department. Same here with the y. It's Bernoulli, 10%, maybe 10, on average 10% of the population or the applicants, sorry, they are applying to this particular university. Now, if the alpha is if the alpha is different than 0, it means the gender is being taken into account in the admission. If alpha is positive, it means that there is a higher probability of the female applicants being accepted. If alpha is negative, is the other way. The same here with beta. Since beta is different than 0, it means that the department choice is affecting the probability, which is usually the case. If beta is positive, then this means that there is a higher probability of people being joined the arts and humanities, you're being accepted in the arts and humanity, and be negative otherwise. Now, to be clear, we are kind of not vouching or saying that this is the truth. I'm just trying to show and instantiate that this is something that could exist in the world. Usually it will be a more complicated function, but this is an instantiation of a SCM star. We're operating, note here that when you're operating in the right side, that is the causal graph side, we don't have what is the underlying f sub y in this case. We don't have the f sub d. We don't have the ux, ud, and y, and so on. We're just operating some type of qualitative level of how these variables are related or possibly related. One observation here about notation, note that the arrows here just mean a possibility of argument. In the graphical model, this is graphical model's basics, but in the graphical model, the assumptions are not in the arrows. The assumptions are in the missing arrows. Then here, having the arrow allows us for the possibility of being zero. Not having the arrow means that it is 0. Then you don't have a leeway to put the value. In one possible case of discrimination, people could be trying to understand, given that you don't have access to the left side, where there is alpha is different than 0, which in this case corresponds to this arrow from x to y. Okay, that's one example. Given that you don't observe, after thinking about this possible SCM and constructing the graph, having the graphical model, maybe you do observe data. We could collect data from this process, and from the data, having the data that is coming from data that is being sampled from this process that is unobserved, maybe you can realize that the TV, the total variation, when you have these two levels of between x0 and x1, when you are kind of changing there in the gender, the variable y will change in this way. Y, the expected value of y given x1 minus y given x0 is less than 0. It's a negative number, which means in this particular case that female applicant is predicted to have a lower probability of admission compared to their male counterparts. Now, for sure, in our framework or in reality, the question is like, or as the Supreme Court dictates or dictates here in the US or suggests broadly, and this happens by the way in the EU as well, in Europe as well. I believe that should happen in other countries, given that usually you follow the same kind of principles that is coming from Rome and things in the past. But anyhow, Rome or England. Is this enough to conclude that female students at Berkeley were discriminated during admissions? Then you observe some kind of statistical disparity, and you are trying to understand whether this is sufficient to make the case that the university is guilty. Second example here, again, I'm trying to connect the idea of the SCM with the graphical model. COMPAS that we discussed Northpointe, that is the name of the company, are trying to predict whether a person will recidivate, I believe, or will offend after being released. Variable Z represents the age, variable W represents prior convictions, and variable X represents race, where X is equal to 0 for white Caucasian and 1 non-white. Now, this is, I'll not parse bit by bit here, but this is the possible structural model, possible SCM M star for all these variables. Now, in the right side here, you have the causal diagram. You have the causal diagram encoding these relationships. For example, X, there is no other observed. In the left side, usually is the hint here to get who are the set of observed variables that have to have an equation. Then there is no other variable that is observed that is deciding the value or affecting the value of X, the race. Then there is no incoming arrow, at least for any other observable Z, Y, and W pointing to X. Variable Z, that in this case represent age, also there is no sort of observed variable here, which means that there is no incoming arrow from any of the Y, W, and X. Note here, interestingly, different than the previous case, there is this unobserved variable U that is shared between X and Z. This is the case that the UX intersect. Remember the construction. UX intersects to Z is different than empty, because this is U here. Then we added our friend here, our bidirected arrow, saying that there is some unexplained source of variation between race and age, at least based on this granularity, or the granularity of the slide to cut reality here, based age, race, recidivism prediction, and prior conviction. And you can go on, such as, for example, the variable Y is possibly affected by X, W, and Z. Then there is an arrow pointing from X to Y, allowing for the possibility, one from W to Y, the other from Z to Y. Then this is the causal graph. Again, this is the truth that is unobserved. We have to collect data from this truth, and the data analysis reveals that the EO, now you're in the equalized odds, trying to compare the false positive and the false, I'll get maybe later in more details, but this is the false positive and false negative when we change the race, when you move the race from the non-Caucasian to the Caucasian, flipped here, sorry, from the X0 to X1. This is the variation that we are trying to understand. And it turns out to be greater than 0 in this case, after doing the analysis, using the data. And in other words, the false positive rates. The false positive rates is higher in the non-white group compared to the white Caucasian group. Then this is what this is saying here. The X1 is greater than the X0. And then the question for us, this is in the observed disparity. And can you conclude that the Northpointe software has discriminated against the minority group, in this case, that are the blacks or the non-whites? That's a question. My third and last example is coming from the UCI data set. The US Census data records whether a person earned more than $50,000 per year. That is the variable Y, 50K. The census also records the age, that is Z, the gender, 0 is male and 1 is female, education level is W1, and the employment status, that is W2, where we have different status here, means different types of jobs. Now, you have the SCM in the left side, the M star, and I'll not parse that in one in particular, but we'll operate with it. And we get the causal graph in the right side. Here we have two variables in the middle that are called the mediators that are affected by the gender in this case. Now, and this is the truth unobserved. Later on, when you get slides, we can go on and try to construct from this guy, or from the understanding of this guy, or for thinking about this guy, how to construct this thing. We never have exactly what are the particular forms. Now, that's the UCI. However, we could collect data from this process, as we did, and the data analysis reveals that the total variation, that is the E of Y given X1 minus Y given X0, less than 0, which means in this particular case that a female employee is predicted to have a lower chance of higher income compared to the male employee. Now the question here is like, is this enough or is this sufficient to conclude that females are systematically discriminated in the various countries, in the various companies in this particular country, in particular in the US, in this case, for this data set. Now, in this case, if you plot here what is going on, plotting the TV y given x1 minus x0, you have this 18, the disparity between these two groups, the total variation or the parity gap equals to 18.2%. We'll come back to this particular example later on. Now, we have seen these many examples so far, and they have some kind of common structure that I would like to put together. They fit very nicely one particular causal diagram, that is this one in the right side. The way to think about that is like this variable. Usually we have 4 sets of variables. One set of variables is called X, that is a protected attribute, or could be a set, but let me call the protected attribute X. We have the variable Z, that is the demographic variables. This would be the other ones that are not the protected attribute, such as maybe age, religion, and so on, if you are considering gender as the protected attribute, or income, or socioeconomic status, or religion. The set Z, this is allowing for the correlation between them. You have the variable W, that is a collection of mediators. In this case, in the case of the UCI Adult, would be the education level and the education level and the type of job that the person is doing. And you have the variable outcome Y, that is in the Berkeley is the admission, in the COMPAS was exactly if the person will reoffend, and the UCI, it was about the salary. And the observation here is like all these models can be projected or can be represented through this kind of template type of model or generic model that is in the right, that we call in this paper, this is the reference here, this is our first paper in the fairness space, trying to solve the problem. We call this the standard fairness model, that standard in the idea that is a good template that you can represent arbitrary structures through some transformation here. It's obvious how to do in these cases. This is just a subset of this one in which Z is equal to D and there is W is equal to empty. This one, the COMPAS in particular matches the example. Then you can have a mapping, a one-to-one mapping. And from the UCI, essentially you have the W1 and W2 being collapsed in the standard model. Now, that's good. Now I would like to articulate the idea. I'm slightly late here. Did we start at 7 exactly, or you have a little bit of leeway? Huh? It's someone answered to me this while I kept speaking. The fairness analysis, I would like to go to the second part and just articulate briefly the idea about what is the fairness analysis through causal lenses, or putting the pieces together of what we talked so far, and what could be a way of thinking about the pipeline from the beginning to end. The first thing that we have in the whole discussion is about acknowledging or understanding that we have this unobserved collection of mechanisms. That is the SCM, that is a good model for that. Now, step 2 that I'll discuss much more in the second part, but I would like to articulate the target measures of fairness. And what I mean by that, at least so far, is like there is the different types of relationships that we could consider between the protected attribute and the outcome variable, depending what is the law of the land, depending on the case, if you want to be in the disparate treatment or the disparate impact, or which kind of business necessity you have, or depending whatever is the context of the social and legal context that you have different measures that we like to consider with respect to this true reality. Just to give one example for concreteness, easy one that will be, for example, a disparate treatment that is trying to encode that the protected attribute X doesn't have an effect in the variable Y. Then someone cannot, for example, in the case of admissions, cannot immediately look into the gender or the salary. The UCI cannot look into the gender and decide to put the salary, a lower salary. This will be a more disparate treatment. And conceptually, what we are trying to encode, that X cannot be an argument in the function of Y in this case. Now, there are different ways of realizing this notion of X not being the argument in the function of Y, which gives rise to different measures of fairness that I will talk in the second part. But that's the idea. You first need to see what's the target measure that we have. Now, the third step, we need to collect data, is an important step. You collect data from the past decisions in which the analysis will be performed on top. That is kind of some type of, yeah, anyhow, it's enough, they give you my time. Now, the third step, we like to construct or articulate a causal graph encoding the assumptions about this unobserved reality. That's how the causal graph comes from. I give you one particular example that is the standard model. Could be others, but this is articulate the assumptions about this underlying reality. And the fifth step is trying to tie these things up. That is, we like that when you combine the assumptions with the data and you do a computation that we say compute the empirical measure, we like this empirical measure to be capturing the target measure that we decided or the law maybe required us to follow. And that's the idea, putting the pieces together here. I want to go to the Q&A. First, everything together. The first step, you acknowledge the existence of the causal mechanisms which are almost never observed. There's a space here. Second step, we articulate the target measures of fairness based on the social and legal requirements. Now, then you collect data from the past decisions, and you construct a causal graph encoding the assumptions about the underlying M star, structural model M star, and then we'll compute the measures based on the data. We already kind of understand quite well, and I would say at some level, what are the mechanisms or how the mechanism comes about or come about. We also, I think, in some natural way can understand what is the data from the past decisions, and we also understand what is the causal graph in some way, or the relationship between the SCM and the causal graph. What we didn't understand is about this particular step about how to articulate the target measures. I'll talk about that soon after the break. And you also don't understand about what are the empirical measures of how to compute these measures. Then tying these two steps, 2 and 5, this is what should come. Should I stop now? That's the, or I have my 2 minutes or 3, or stop is better. Drago or Justin?
I would say stop, and we can discuss some questions that have been asked in Slido in the meantime.
Okay, you have questions. If you can read it or pose it, I'll be happy to take it. Thank you, guys. I will stop for 5 to 10 minutes, guys. If you want to ask questions, otherwise you can get a drink or go to the bathroom, or feel free and try to come back in 5 or 10.
Yes. So there are some questions. So Severin posted a question about why does the standard model look the way it does, and are there alternative models to the standard model? And I guess, Elias, you can take this question.
Yes. Why the standard model looks in the way, I'm not sure if you don't like the face of the standard. I think it's kind of cute, but it looks in the, this is a joke. I like how it looks. Why? It's a tough question, what it means, why it, but I would say the main idea is like, let's focus on, let's say that there is no, there are 4 clusters here, as I said, right? There are the 2 most important ones is the protected attribute, the cluster related to the protected attribute, and related to the outcome that is related from this X to Y. Now, this is grounding. We don't have an option. Any possible model that you like, or any possible way of encoding the underlying SCM, we'll need to allow for that. Then this is the X side and the Y side. Then in some kind of generic way, there are 2 other things that could be happening. There are variables that are correlated with the protected attribute and they do not come after. They are not affected by the protected attribute. Then this is why you have this part of the graph here between X and Z. This is just correlations that are happening. There's no causal explanation. There's unexplained source of exogenous variations between X and Z. And there are the variables that are affected by X and Z itself that are what we call the mediators. And in some ways, just encoding the nature of the world, and those are the kind of most elementary or most, I think, coarse way that we could encode any possible causal model. Now, obviously, this is it's quite powerful, not getting in all the details, but in some way, for sure, you could have more granular. You could operate at this level here, in which W1 and W, for example, W1 and W2 are not the guys that are collapsed, but he's kind of in this way that you separate them. And then you say that maybe through this path, X, W1, and Y, it is okay, for example, to use occupation, but it is not okay to use whatever other variable that we have. One is employment. It's okay to use education, but it's not okay to use the type of job, for example. Now, we are in the standard model because the analysis get much more involved when you start talking about, we are kind of opening up the standard model. Then this is just the first template that one could think that that is easy to operate, but there are more refined models. You can check our paper. One example of operating on this way, check the paper with Zhang, with Justin Zhang and Bareinboim in UCI 18. I forgot the title, but I think it's non-parametric decomposition or some variation of that. That the UCI 18 with Justin that shows how to operate in this kind of broken down, more fine-grained, I should say, more fancy to say, more fine-grained type of models. But for the sake of our discussion, we operate with standard model. I think it is good. If people already operate in the standard model, this already will be a big advance. Next, Drago. I hope that I answered the question. If not, let us know.
Thanks. There were also two questions. I think they're very similar, and that is, can the causal graph handle feedback loops? So can you have connections that go back and forth, and how would you handle connections that go back and forth?
Yeah, the model here that we're discussing, at least the standard model, how we represent it, no, we don't have feedback loops. This is a DAG, a dialectic acyclic graph with these two different types of arrows, directed and directed and bidirected. In general, you could, at least this is what we do in causality in general, if there is some kind of temporal reality that you have the different time slots that you are thinking about. By the way, assumption here, there is no causality that is immediate, that is like X is causing Y and Y is causing X at the same time. And the assumption is like, usually you can space that in time based on physics. Then you could open this graph and just kind of index in time, and then you could have time series and do the analysis on top of, let's call the sequential standard fairness model. Then it is possible in principle. In practice, based on my experience, it can be really tricky or really involved, but we can talk about that offline. It's possible conceptually, hard to implement, but can be done. Thank you.
Good. Thank you for the answer. So I think the person who posted the question likes the explanation.
Okay, thank you.
Good.
Okay.
So the question one, I think a smaller follow-up question is, why would you not always want to operate in a more fine-grained model? So why would you do the compression and grouping of the W or Z variables in general?
Yeah, that's a good question. I personally would prefer to operate in the most granular model, because I think is the motivation for your question. I think you are in your instinct is right. It's more informative and it's nicer in some way. There's no loss of information in some sense. Not that whatever, there is some tension here how you operate in the cluster or the cluster or not cluster mode. But in practice, why you wouldn't? Because depending on the setting that you have, sometimes dozens or hundreds of variables, can be hard to construct the model that is the most granular one. And it is not easy, but it is easier to construct the standard model, because essentially we are just trying to decide the X and Y are already given. Then for all other variables in the system, we are kind of trying to decide if you put in the Z bucket or in the W bucket in some way. Then that's why you wouldn't. But if you could, I would recommend to operate in the most granular way. And the other thing that I would say is, like, for sure the discussion could be in court that you operate at some level, get a result, and then someone could say, oh, we are getting this result because of this, because it's collapsed in some way, and the refinement could be open up the graph or the parts of the graph that you don't agree for a subset of the W or subsets of the Z, and continue the analysis with this refined model. Then I can see that there is a process of, we can envision that there's a process of refinement depending on what you want and how the argument goes from both sides. Then the short answer is, like, yeah, let's do the refined if possible. Let's operate in the cluster way if not possible to operate the most refined one.
Okay, so the last question that I think is definitely worth mentioning before the break, and I just want to say that thank you to the audience, because the questions are very much related to the causal literature. And one of the questions is, so the DAG does the DAG have to be given a priori, and can the validity of the DAG be proved? And I think Elias can also take this question. So
I didn't get the first part, the validity of the, what's the first part of the question? Can the...
So the DAG you have to construct yourself. The question is, can you prove that you have a valid DAG? So is there any way of proving the DAG? I think that's the main part.
Yes. I wouldn't say that there is a way of proving the DAG. There is a way of testing the DAG, or trying to falsify the DAG. As in any scientific kind of claim, there's no way of proving, or at least empirical claim. There's a way of getting some confidence based on a collection of tests that maybe the claim seems to be right, and then you can keep getting confidence based on piling up more tests against the model. And then the answer is yes, we could get some of these models, and kind of each of these models I didn't discuss here, they have testable implications in the data. Then once you say there is the underlying SCM, there is the causal diagram, and now I go to the causal diagram, there is ways of getting different types of constraints that the causal diagrams implies in the data. Then the most classic one is condition independence. There are equality constraints, there is inequality, there is polynomial, there is other types of constraints that these models imply in the data. Then from the model, you can go to the data that is coming from the SCM and check if it's true. If it's not true in some way, or if you cannot at least have some confidence that it's true, then this means that the model needs to be rectified, or should be updated. Again, if it is true, it doesn't mean that the model is right. It just means that we couldn't falsify it. But this is kind of one of the features of science, I would say, in the way that we understand it for the last many years. But yeah, that's the idea. There are testable implications. And the other part, I'm not sure if this was the question, some people could try to do, is not uncommon, that they can use the same type of constraints, or the quote-unquote testable implications that are constraints. You can try to go the other way around and induce a causal graph if you didn't have one. That this is called, a huge literature in causality, called structural learning. Turns out to be a hard task. It's possible to learn or the causal graph or equivalence class of causal graphs. But that's a good question. Thank you. I think it's enough, unless there is some last one, or can we move on just for the sake of time?
I think we can move on. I will try to answer in the chats to the best of my ability. Okay. Yes. The audience thing, and sorry for all the questions. There are a bunch of questions, so sorry, I have randomly selected a couple, and we hope to answer more in the Q&A after the second part of the tutorial. Thanks.
Yeah, thank you guys. Thank you, Drago and Justin. Now I would like to go on and do what I kind of promised about analyzing the disparities, or analyzing the demographic disparities, in this case TV, and going back here to the UCI Adult data set, that you have the set Z, that is age, again, age and nationality, the set W, that is education and employment, X, gender, and Y, salary. Now, we call from the beginning that you have the observed disparity, that is TV, when you move between the values of X0 and X1, between the genders, and you observe in Y that there is some kind of, apparently the salary for the female employees are lower on average than their male employees. I think the number was 18.2%, some kind of on average. And the point is, like, this variation could be explained in different ways. One possible way is maybe the company is blatantly wrong or evil, I would say, too emotional, but whatever, it's blatantly wrong, that they are looking into gender and directly changing the salary and penalizing the female employees. That's one possibility, one possible explanation that could account for the difference in TV. Another possible explanation is that gender is used to infer the age or the nationality, and the age or nationality are being used to decide the salary. Then this path here, this variation is the one that is accounting for the differences in TV. And then you have a third possibility, that decisions of the salary decisions were based on the education or the employment. But education and employment, even though it's not control of the particular company, but is affected by gender in this society. Then this is this possible variation here that could be happening, accounting for the difference in TV. Then very important, if you watch this or check this out, this is a very important slide that is kind of including the core here. Now the core of the tension, and the tension comes from the fact that it is possible in this particular, it is okay or kosher in this particular society that variations due to education, that are this one here, variations of Y due to X that are explained to education, let's say that is this one here, are okay, but it's not okay the difference that are directly due to gender. And it's also not okay to use the variable age of nationality as a proxy for gender, that is these variations here, and ended up penalizing some groups. Then that's the core here. There's a tension between the TV and the different explanations of how this TV could be coming about or could be realized in the world. And in my view, or in our view here, Justin's views or Drago's views, is like the questions are how do you disentangle this composite measure or this TV that is what is coming from the data, and how do you disentangle this guy and explain which mechanism, what are these three different mechanisms, how are generating the disparities in TV. Some of them are maybe okay, some of them are not okay. It depends on the social, legal, and context that the situation is being discussed, or the society. Now, this will be the topic. We are trying to understand how to do this disentanglement. For sure, then, a hint here from the first three examples that we have, it is not enough to say the TV or the EO is not balanced or is different than zero. Sometimes it's okay, sometimes it's not okay. We need to connect, this coming from the Supreme Court. We need to have the causal link or the causal connection between the observed disparity in the composite measure, the TV, and connect and establish the causal link with the underlying mechanisms. That's the exercise, but this is the fundamental problem here that we're trying to solve. Now, I messed up here. I may be late 3 minutes or 4. This will be the break. I'm coming back from the break. Hello, guys. I hope that you have a good break. You have some good coffee. Give me 1 second. It's 7:54 here in New York. I'm waking up. Now, this is what we saw before the break. Now we are trying to understand how to do the disentanglement of these different the variations that are in TV. And variations, by the way, it means that we are trying to explain how this variable Y is changed. This is a random variable. Those are random variables, Y, X, Z, and W. We are trying to explain how variations of the variable Y due to X can be mapped to these different mechanisms. And by the way, that follows very naturally from the standard model. We're essentially capturing the three general or generic type of mechanism that is direct, indirect through this mediator, and indirect through the confounders, as we call, or the set of background variables. Now, in order to do that, I need to define just one more thing here in the, how can I say, 101, causality 101. I need to define the notion of counterfactual. Now, I'll define, first to define counterfactual, we need to define something called the potential response. Now I have two sets of variables X and Y that are endogenous variables, i.e. subset of V. The potential response of Y to the action do X is equal to X, small x. This means that do X means equal to X means that you go to the original system that there is the X is equal to the f of X, and you replace the X with the f of X with this constant small x. This is what action do X means. And let me start here. The potential response of Y to action do X is equal to X, denoted by notation here, Y sub X for the unit U is equal to small u, is the solution for Y of the set of equations in the model. Our data generated model is M star sub X. M star sub X is just the M star with the function of X replaced by the constant. In other words, if you want to see what's the semantics of this operation, of this meaning, Y sub X of U is equal to the solution of Y in this system M star of X for each unit U. Now you're ready to define what is this counterfactual. Again, we have this subset of variables X and Y observed, endogenous. The counterfactual sentence, the value of Y would have obtained had x being small x for unit u is equal to u is interpreted as the potential response y sub x of u. I'm just binding the y sub x of u that is defined here as being the value of y would have obtained had x being x for the unit, particular unit, u is equal to u. Then stick with me here or bear with me because well, we'll spend maybe a semester discussing variations of that during the class. I'm just giving you a kind of brief idea. Hope it's clear. If not, just think a little bit because whatever, it may, if you're not American, even it's not a direct, this is a conditional here. Would have obtained it, had something, some kind of model statement here. But now to use this idea, I would like to propose or outline a thought experiment that goes as follows. Going back to the UCI. For a male person, meaning x is equal to x0, the question that you would like to answer is like how his salary y how would his salary change, that is y, had he been a female, x is equal to x1, while keeping the age, nationality, education, employment status unchanged. Unchanged means at the level of x is equal to x0. How would his salary change had he been a female while the other set of variables being unchanged? Now, maybe a tough sentence to parse. Let me try to use some graph to give an idea what this means. And again, I would like to focus on the variations here. Note here, let me just put some, note here that we have the variable y, the difference between, this is the variable y, then you say how y will change had he been a female, he is a male. Then in the natural world, in the natural meaning, in the actual, I do not we call natural as well, or in the actual or natural world, the guy is a male. Then for the variable y, x is equal to x0. For the variable z, x is equal to x0. For the variable w, x is equal to x0. And this is the natural or the actual world. Now we would like to contrast that, or we would like to evaluate this sense. How would his salary change y had he been a female, while keeping the other things unchanged? Then we like how the salary will change y had he been a female, that is x1, while keeping the other things unchanged. Then for the sake of z, that is age, nationality, he is still a male. Then the connection between x equal to 0 and z is not changed. The connection between x is equal to 0 and w is not changed. But for the sake of salary, you like to understand, I'm repeating here because it is non-trivial to parse based on my experience, how his salary will change. That's why had he been a female, that is this x1. Now, we like to contrast the situation, reading in counterfactual notation here, this particular graph here that is the natural or observational one, the value of y. Now we already have semantics for counterfactuals, that is the subscript. The value of y had x being x0, w and w being whatever value w would have been. This is big W here, is not small, it's a variable. Had w being given x is equal to x0, given that the guy is a male, versus the value of y had x being equal to x1, had he been a female, and w being whatever value it would have been had he been a male. That is this w with x0 here, given that in fact he is a male. Then, well, I'll go back here, another example, but that's the quantity that we want, or the experiment that we would like to make. Note here that for this particular experiment, the only things that is changing, the things that are not changing, this relationship here, x0 zy, x0 zy, x0 wy, x0 wy, this is not changing. Then we are doing a minus here, which means that these guys are canceling, or these variations are discounted, are the same in both sides, left side and right side. How y is changing is essentially based on this x1 versus this x0. This is the only thing that is changing between them. Now, what does it mean? This means that in reality, we're encoding the notion of what we call in this paper with Justin, that called counterfactual direct effect. That we are just speaking these two guys here and putting the expected values. The counterfactual direct effect of x is equal to x1 on the outcome y relative to x is equal to x0 in a situation where x is equal to x, in our case x0 is, and you're just copying these variables here. Y had x being x1 and w being whatever value it would have been had x being x0 minus y given x0, comma y w having whatever value being x0. Then try to parse it, but that's the idea of the counterfactuals, that essentially, again, we are kind of canceling all any paths, and the other way, the only variation that y is able to get is this variation through the direct link from x to y that is changing between genders. Then this is the notion of direct effect, and you are removing this effect because it's the same, and you are removing these variations here. And this is the counterfactual direct effect. For simplicity, I use DE here. Variations between when x0 move between x0 from x0 baseline to x1 and y given x. Now, one interesting property here for this counterfactual direct effect to test the null, this is kind of sanity check. If y is not a function of x in the underlying SCM m star, then it turns out that the DE, the quantity that you just defined, will be equal to 0. This is just sanity check. Again, I think we are trying to relate this structural measure, this qualitative thing, with something that you may be able to measure. Then you are saying if y is not a function of x, this the notion, the direct effect that we are introducing here will be equal to 0, which is expected. Now, observation. If anyone, there are different ways that you could define many of these quantities. I think this is what maybe the most granular that we have, but whatever, for each notion, this is basic filtering. If someone is trying to capture the variations of y that are due to x, this direct link, we'd expect whatever quantity they put, if x is not a function of y, whatever name they give, you expect to get this equal to 0. Otherwise, whatever, it's hard to say what we are really capturing. That's the... Now I'd like to do a second thought of experiment here, that is for a female person that is x is equal to x0, how would his, for a male person, sorry, if x is equal to x0, how would his salary y change had his education and employment status been at the level of a female person x is equal to x1, while keeping the other variables, age, nationality, and gender, unchanged at the level of x is equal to x0. Now I would like to do the following, to think about the following quantity here. Next, let me read it here. I'm trying to construct the value of y had the education and employment, that is w, status being at the level of a female person. Now, in some way, I want the w to be varying between females and males. The male is a baseline in this case. Then for w in the natural world, x is a, by the way, let's ignore the x0 here, because they are the same in both sides, because it's a male person that we're talking about. You could flip, if you want to put whatever, you could flip the labels. Now we have x0 here. Now we like to understand from the w perspective, originally or naturally the person was w is equal to x0, then the value of y had x being x0, that is this link here, the value of y had x being x0, and the value of w being x0, that is the baseline, versus the value of y, this is the same. Change had his education employment status being at the level of female person, that is this x1 pointing to w here. That is this w sub x1 here. Then that's the quantity that we want, naturally, or the same way that we did in the first experiment. When you discount this one, or when you subtract one from the other, this path here is the same. This, or the source of variations, these source of variations are the same. The only thing that the only type of changes that y is feeling is the one that is going through here. That in one case, y believes that x is male, and the other case, sorry, w believes that the person is male, that is x0, and here w believes that the person is female, that is the x1. Again, that is this sentence in blue here. Then that gives rise to the notion of what we call the counterfactual indirect effect. Then counterfactual indirect effect of x is equal to 1 on the outcome y relative to the baseline x is equal to x0 in the situation where x is equal to x is, and then reading here, we're like given x, y had x being x0, y given x being x0, this is one, y given x0 and w being whatever level it would have been had x being x1 and w whatever value it would be that is x0. For sure these guys here, they are matching in some way. This is why it is the natural world. There is no conflict. This is not matching in some way. This is called the nested. Also, the name is, this is a nested counterfactual because we are talking about the world in which y have some value of x and w has in another world that w has a different value. There's some kind of double replacement here if you go through the algebra and the way that this is operationalized using the axioms. But anyhow, that's including the notion of the variations that are due to the indirect effect, or these ones that are coming from W. Now, property that you like from this quantity, analogous to the CTF-DE, is like if y is not a function of W, and if W is not a function of X, in the underline M star, then you get this IE is equal to 0. In other words, we can check. In other words, if in some way you have a way of computing this IE from the data, and if this is not equal to 0, you can say that this will not happen. That maybe y is a function of W, and W is a function of X. The same way that you can do with the direct. I forgot to say. If this guy's DE is not equal to 0, then in some way you can say the other way, that y is a function of X, despite the fact not having it, despite the fact of not having the M star. Now, my last thought experiment, last thought experiment here. For a male person that is X is equal to 0 and a female person X is equal to 1, how would their salary Y differ had they both been male persons? It's a different one. Let me read it again. For a male person, X is equal to X0, and a female person, for a male person, X0, and for a female person, X1, how their salary Y differ had they both been male persons. That is the X1. Now, how do you do that? This is for the male, sorry, X0, this is for the male person, and for the female person, we would like to say how their salary would be, Y, differ had they both been males. Then this is Y sub X0. The value of Y had X being X0. The value of Y had X being X0. Given that they are males and they are female. And there's a different contrast that we have before. Now, if you want to see graphically what this means, this is like X0. Let me see the difference here. Note that this is the same because this is person is naturally X is equal to 1, person is naturally X is equal to 0. But now for the Y sub X0, or in both cases, for the Y side, X is equal to 0, X is equal to 0, and given that X is equal to 0, this also cascades to the W, this also cascades for the W. Then whenever what we're highlighting here in reality is that what is changing between these two sides, these guys the same because Y sees X as being 0, Y sees S as 0, W sees S as X0, W sees S as X0. Now, Z see X as 0 here, but see X as 1 here. Because the person is a female here and is a male here. Then this is the contrast that we're in reality capturing. Then this gives rise to the notion of the notion of spurious effect. And it's spurious because it's encoded the paths that are not causal. It's not downstream from X, but it's these paths here that are the variations that are being accounted or you're trying to compute in Y. Now, definition, counterfactual spurious effect of X is equal to X1 on the outcome Y relative to baseline X0 is equal to Y sub X0 given X1 my Y sub X0 given X0. Okay, those are the quantities. We expect to have some type of sanity check here as well, that if I'll just do it quickly, but if this path, if there is no variations that are due through this spurious effect or the backdoor paths, as we call, we expect that SC is equal to 0. And maybe there is a way of testing for that, despite the fact you may not have the M star. Now what I would like to, now we have 3 different quantities that is kind of connected with the direct, the indirect through the W, and the spurious through the Z. We have well-defined quantity in terms of the written in counterfactuals and in terms of the M star. Now I would like to introduce what we call the how much time do I have, by the way? It goes until what, Drago? Just to see how much I can speak.
So I would spend another 8, maybe 10 minutes on the presentation, and then I would do 5 to 10 minutes of questions.
Thank you. Now, I would like to try to connect that with the data in some way. Now, and this is the theorem. The total, the data is the TV. Now, I would like to connect the TV. Could be the total variation between X and 0 that when you move between genders and the effect on Y can be written as this thing that the TV is equal to the DE, let's say plus, but there's a minus here that we can discuss, plus IE and SC. Then there's a way of connecting these three different quantities with the observed disparity. How do you do that? I'll do it quickly, just given the time, but I'm just putting here, this is just the Y given X0, the natural one. We're not changing any arrow. And this is just the one that, if you recall, you can go back in the slides, a few slides back, maybe 4 or 5 or more, maybe 7 or 8. This is the one that is encoding the DE, because the only thing that is changing here is this path. You go back, you already defined this quantity, then this is the DE. Now, if you just copy this guy here, just copying this guy is the same as this guy, I'll just call this the remainder. I'll just note that this guy minus this guy, this is the X0, Y given X0, Y given X1, this is the TV. This guy minus this guy. And I'm putting minus this one plus this one. Then these guys are kind of canceling. This is just a way of saying TV could be written in this minus that. Now I want to put a minus this guy plus this guy, and I'm just doing a proof by picture here. And if you note this guy, this world minus this one, it turns out to be equal to DE. I would like to try to see what is this world here, this guy minus this guy. Now, what we can do is just copying here. It turns out that this one minus this one, we already discussed, is equal to the IE. And this one minus this one turns out to be equal to the SC, or the minus, the flip of the SC. But the SC, let's call the SC. If you do this one minus this one, the SC. Then this was the remainder that we said, that you can see, because this one is the same as this one. Remainder was this minus this one. You can go on and do the variation. But the observation here, just putting everything together, is TV is equal to the DE, that is this part here, minus this part here. That in this part here, you can do at home and do is equal to the IE plus SC. Now, that's very nice, because we are able to relate this high-level kind of quantity that is purely statistical disparity, that is TV, you are able to relate that with the counterfactual quantities DE, IE, and SC that have a clean interpretation in terms of the underlying causal mechanism. Still, you don't have a way. We have one, if you want, we have one equation and 3 unknowns, because this is constant, it's coming from the data. And now I have these 3, I'm trying to see how much variations of this type, how much variations are this type or this type. Then you have 3 sources of variations, one equation and 3 unknowns. Still hard job. Now the question, can you get these quantities from data in some way? Turns out that you can. There is some kind of identification formula for that. Under the standard model, and someone asked about standard model, why you do standard model? Standard model, you're getting a positive answer. Depending on the model, it can be more tricky. It's not for convenient, I'm just stating a fact. Under the standard model, DE, IE, and SC are estimable from observational data the observation data from the past decisions without having access to the the M star, P of X, W, Y, and Z as follows. I'm not parsing here, but the D is equal to this expression, I is equal to this one, and SC is equal to another one. Note here that this is the structural measures with respect to the M star, well defined in terms of the mechanisms. All the guys in the right-hand side, those are the empirical measures. In other words, they are functions of the data, that is the P hat in reality of X, Y, Z, W. In other words, what I mean by that, there is no subscript here. If you go one by one, bit by bit, there is no subscript here, which means that is exactly what this is the meaning. It's a function of the observed data from the observer of the natural world, called natural. Now, just connecting here what we're saying, by the way, this is the fairness measure that is on the top, that is the left side here, and you are connected with some kind of empirical measure in the right side here. Then the link between these guys, the 2 and 5 from many slides ago, is established in this case. Then kind of success in this sense. Let me just ground that. But the result is there in the paper. How to derive that and more details. Now, for sure, we can go back to the data set and try to evaluate these expressions that are given here in terms of the UCI data that we have, that we observe some disparity, this 18.2%. And then you can see here that most of the variations for Y are happening due to the CTF, i.e., due to this path here, X, W, and Y. This is just a different way of showing. And in this particular case, excuse me, in this particular case, at least we agreed, just for the sake of example, that was kosher. It was okay to get Y could be varying due to X, due to education and employment. It was not kosher or not taref, or it was not okay, the one through gender or the one through age. And maybe you can say that there is still something that it's true, but anyhow, the majority of the variations in TV is coming from the IE. And you can have a question about how much you accept of these derivations, the variations, but mostly it's through IE that seems to be okay, or it's okay. Now, I'm almost done. I like to just quickly connect the idea about the disparity that we analyzed so far is about the disparities in the TV or demographic parity or the gap, parity gap. Here, this is more decision-making kind of setting, but we also can have disparities in the prediction error rates in the COMPAS, for example. Then, and slides are available, will be available, then you can check. I'll just give the idea here. But in the COMPAS, maybe you are trying to predict whether the person will reoffend or not, and you are using, maybe you are training the classifier based on age, race, and prior convictions. Now, this is the prediction that you have whether the person is reoffending, and you have a a Y star that is the true, whether the person did or not reoffend. Then note that this guy here, or these variables here, this is the original causal diagram in the real world. And this one is the one constructed with the Y, that is the one constructed that is coming from the classifier that you may be building or someone built. Then Y star represent whether the defendant actually reoffend. Y1 is if he reoffends, 0 is otherwise. We'll focus, and I'll just do it quickly again. We'll focus on the EO, equalized odd between X0 and X1. This is the kind of EO form, which, let me just give an example. We will, when you move between races X0 and X1, let's say that Y is equal to 1, that is the person reoffend. We are predicting that the person is reoffend, that is this Y, given that Y star is equal to 0, that the Y star is equal to 0, that the person didn't reoffend. Then this is called the difference in the false positive rate in the classifier. And you like to check this happens, and you like to know the same version, but given is this happening differently depending on what is depending on what's the race of the person. There's a whole discussion. This new RIPS paper, it was at the end of the year in 2018. That is the way of showing how to decompose now not the TV but EO in terms of the same kind of ideas. It will get more involved because because in reality, the quantity that we have, it's always conditioned on the y star. Then we have some type of, we are trying to check something related to the y, and I'm not doing here the step by step, just want you to have available, but where we can try to get a direct effect, just changing the direct in the same way that you change this is y sub x1 and y sub x0 and the rest the same. But now note that we have a complication that we are conditioning the y star. That is the true, what the person did in reality. Then you are kind of opening, if you know something about causal graphs, if you don't, totally fine, but it will get involved because there is conditioning involved in the quantity as well. But anyhow, we can still define the quantity EO direct effect, that is this one here, whatever it means, that we could go, it's the same kind of in spirit. Let me jump here. How do I do there? 1 second. No. I just want to jump. How do I do that here? I can do one by one then. I don't remember now. Oh, show navigator, because it's in the other screen. Now we could do something similar and get in some kind of explanation for the EO. There is a decomposition for the EO as well. And you can get, the identification will get more complicated. I will skip that. If you want the details, go to the paper. There is some issues about doing feature selection, about which kind of covariates you can use when you are constructing the classifier Y. There is some kind of restriction that you cannot use mediators. And there is some kind of procedure discussed in the paper on how to do that. Now I would like to conclude the well-founded disparate treatment and disparate impact claims require the plaintiff to establish a causal connection between a defendant's policy and the statistical disparities found in the observed data. From the SCOTUS, means Supreme Court, SC, of the United States, how they call SCOTUS, no fairness claim can be made without solid causal support or solid causal underpinnings. Then we need to establish this connection. Now, we introduce here a framework or a set of ideas and principles and graphical conditions, a framework for fairness analysis based on true causal lenses to support such claims. In particular, we introduce fairness measures based on the counterfactuals that are, I believe, meaningful, transparently, and easily associated with the underlying causal mechanisms. We proved, or at least I showed the theorem, the causal explanation formula, which quantifies the influence of the different mechanisms with respect to some observed statistical disparity. I spent a lot of time talking about the statistical disparity coming from TV. I just give a very quick idea for 1 minute about, you could see statistical disparity in the EO related to these false positive and false negative rates that can be decomposed as well. And we also derived, or at least I showed, that derived identification expressions for the explanation formula, which maps the structural quantities, the DE, IE, and SC, to their estimates and data counterparts, can be estimated from data. The hope here is that these results can help towards the developing of the next generation of AI system that hopefully will be more fair, accountable, and transparent. Thank you in the name of the team, and I will be happy to take questions.
Good. Thank you, Elias, for the presentation. I would, in the interest of time, I would straight away go to the questions. So Elias, if you can switch back to slide number 43, because someone asked about computing the measures in practice. I think if you show slide number 43, I think that would be very useful for someone who's interested in computing.
Can you see the 43?
Yes, I think so. I think that was a question from Bahar. So thanks for the question. Let's keep the slide open for him to see how this is done in practice. And Carolyn asked a question about what we think is the most important, outstanding research questions in causal fairness in your view right now. So what do you think, Elias, are the main challenges of causal fairness in the future that we have?
Right. By the way, that's a good question. Thank Caroline. there are quite, by the way that I'm presenting, I'm trying to show you the result that I'm kind of more round and nicer and more polished in some way. There are questions, but to be clear, there are questions all over the place, and this is why I'm here, to invite you to help us to solve some of these problems. Then it's to be clear here, we are very far from done, even though I think we do have the building blocks, or some of the important building blocks on the table. Now questions, just one in this screen, that there are a collection of them, or many of them. One of them I can get even from this slide here. If you are trying to do estimation, great, you are able to connect these counterfactual measures to the TV in some way nicely, then I can decompose the TV and give this interpretation, and you are able to link each of these quantities with their data counterparts, data in the sense of you have estimands related to these quantities that are given by this one as a function of the PV. Now, question, which could be estimators, or what could be real world in practice? How do you estimate these things? And it turns out to be very hard. In particular, if you have sets of W's and Z, just one obvious kind of quick shot here, but if you have W and Z that are high dimensional, this is already very hard because we are summing over all these combinations. Then if W and Z is already 10 dimensions or 20 dimensions in binary, it turns out to be already quite hard to do. This kind of blows up, obviously, such as in any kind of task. Now you can start trying to be clever, or hopefully be clever to say about how to do that in practice. But this is an open problem about how to do the estimation of this quantity if you are in the high dimensional settings. That's one. The other one, again, I think I gave another one. And Drago, you can stop me if you have other questions. But there is still open questions about, it is true that we have ways of validating these causal models through certain constraints that I alluded to earlier, but it is still open question about how to do a full evaluation or the testable implications of models like that. Then there is still kind of theory to be developed about how to test these models. Another one, the discussion that we have here, we are talking about a particular setting that we call non-parametric. And non-parametric means overloaded word, by the way, be careful. Non-parametric for us means that these underlying functions, the f of z, f of x, f of w, f of y, all the underlying mechanisms, we don't want to make assumptions about the form, about linear, monotonic, whatever kind of form we could have. And then whatever, the analysis is the most, and we don't want because it's the less committal. In other words, it's the most general that you can get. Sometimes you are able to get some results like that, which is good because we are very non-committal about this underlying mechanism. Sometimes in practice, we get a negative answer. And sometimes the result of the analysis for more refined models will be not identifiable. Because this is identification problem means identifiable and estimable to this one. Depending on the model, this is under this G. If you have perhaps a G prime that there is one variation from the standard model, if you need, maybe the answer will be non-identifiable. Then if it's not identifiable, it is non-identifiable non-parametrically, meaning when you don't want to put assumptions over the f of x, f of w, and so on. Now, we don't know how to operate in the fairness when you start making some reasonable, sometimes assumptions about these functions. Then there is the whole discussion about how to do when the underlying system, when the f is linear, or is monotonic, or many other classes of functions, or is additive with some kind of noise. Then very interesting problems that this was saying is just the beginning to operate in this more generic or more general type of setting. There's still a navigation over the space of assumptions. I think it's enough. You can drop me a line if you want other questions that I can share. Drago, do you want to get one more or two questions?
So I think we are running out of time. So if there's one more question, I think we have answered. I think we have captured most of it. So if there's one more question that perhaps we could do, or I think it is good to close. Okay. There's another tutorial coming up as well. So thanks.
Okay. If you guys have another question or anything else, drop us a line. We'll be happy to talk. Thank you very much.
Time for final remark. Elias, closing couple of sentences, please.
Closing couple of sentences. Okay, yeah, I would say, yeah, so I think it's a very exciting area, very exciting intersection between causality and fairness analysis. I do believe that fairness should be done in the context of causality, given that we're trying to connect, or you're trying to connect with the real world and be able to make claims that make sense in the world. Then I think it's a very nice and brave, there's a new world there, and I would be happy to talk more, or would like to see your work in the future. And very thankful again for Tiberio and Zach Lipton that allowed us to talk here today. Thank you very much and have a good day.
Thank you, guys. Thanks for joining the tutorial.
Thank you. Bye.